we are going to make a Bootstrap confidence interval to estimate the hours of TV per day that college students watch. To do that, I'm going to use a sample of data from BMCC statistics students. So I take various surveys of my students collecting data. Here in the box is one particular question where I ask on average, how many hours of screen time do you watch per day? And then there's rules below, include any use of your device, recorded videos, streaming services, games, social media, etc. Include time when you're not fully paying attention. Only include time when you as an individual are using the screen, not a household average, like when it's just playing in the house and it's not your personal device. Include time watching shows or movies outside your home. Give a numerical answer in hours per day. And 0 if you don't watch any. So let's see, I have a link to that data here. And that takes us to this spreadsheet here. So here are the hours per day that my summer students entered. 13 hours per day, holy moly. Interesting, 12 hours per day, wow. So here is a box plot of that. We can see we get a couple of outliers, 2, 4, 6, 8. Google got a little weird on that 13.5 on the end. We probably should fix that. And then down here we got a little box plot from the stat applet. And notice the scales lined up, 2, 4, 6, and so on. So they give us 2 bits of information. We can see 25% of students watched about 4 hours per day. Right, that's this second quarter here. 25% students watched 2 to 3 hours per day. And then this upper 25% of students in this summer class watched more than 6 hours per day. Interesting. Okay. The middle 50% was between 3 and 7, like 4, 5, or 6 hours a day. Interesting. All right, so what I want to use this is make an estimate of what college students in general might watch on average. So I could say on average college students watch 5.38 hours per day because that's the average for the sample, and I'm going to use this sample to predict for all college students. Question, is this really a representative sample of all college students? Probably not. Maybe I should narrow it down to community college students because community college students tend to be a little bit different than your average college student, including universities. So what's my population of interest here? What's my parameter that I'm trying to measure? And then whenever you make an estimate for population, you don't have the whole population. So you got to say, well, there's a margin of error here. So we have to calculate a margin of error. And we're going to use Statkey's Bootstrap confidence interval system to do that. So what I want to do is I'm going to put this data in Statkey, and then I need to take some notes. So let's copy that. And say I don't have Statkey open yet. And we are doing a Bootstrap confidence interval for a single mean. So I want that link. And then we're going to edit in our data. So I'm going to delete the price data of Mustangs here and paste in my data. And notice I have a header row, but I don't have anything in front of the numbers identifying them. So there's no first column, so that's unchecked. Data has a header row is checked. Okay, so that make sure you have those right. Hit OK. Then I should get a summary over here. There are 24 values. Mean is 5.375. Median's 4. Standard deviation's 3.136. And that should match what I have in my spreadsheet. Let's see here. Open that up a little bit. And add a couple more decimal places to match Statkey. 3.163, not 0.136. There's my median of 4. I didn't do a count on this. Let's double check. Count numbers in column B. Oops, and I entered that incorrectly. 24 numbers. Okay, so it matches what Statkey has. All right, so once I get my data successfully uploaded in there, and I'm sure it's the right data set, the 24 values I meant to have, then we want to, let's explain what a bootstrap is. So what a bootstrap is each of the numbers in my list, the computer basically makes it like a playing card of each of these numbers. So a card has a 4 on it, and a 3, and a 9, and a 5, and a 2.5, and a 2, and another 2. So there's multiple 2s, there's multiple 10s, and so on. And then it shuffles that deck and it pulls from the deck one card at a time and it reads the card. Oh, look, it's a 3. And then it writes it down. Then it puts that card back in the deck, shuffles it, and pulls another card. Oh, look, it's another 3. Puts it back in the deck, shuffles it. What is it now? Oh, it's a 5. Write it down. And it's going to do that 24 times to make a new sample based on this. So the only numbers that can end up in the new sample are numbers that were in the original, but numbers can be drawn from the deck more than once, randomly. So if I select generate 1, then what it did is it again grabbed from this deck up here one at a time with replacement, and it got this new sample. It's slightly different. This time we have a mean of 4.729. I can see that mean is plotted right there. If I generate another sample, Statkey's going to reshuffle and draw with replacement from the deck of cards there, and I get another similar sample. This time the mean was 5.188. Notice the original mean was 5.375. Now, I don't just want to do that 1 or 2 times. I want to do this thousands of times. And every one of these dots, if I point to them, is a new sample over there on the bottom right from the same set of numbers we started with. Slightly different mean because it's a slightly different configuration of these 24 numbers right here. And we want to do that at least 5,000 times. In my opinion, it's 3,000, 4,000, 5,000. Let's go 6,000 times. All right. So there's my Bootstrap confidence interval. So basically, I'm saying, okay, I think this is a representative sample of community college students right here, the original, and I'm going to use that to resample to see what variation we might get if this is typical. And this is 6,000 resamples. And now what I want to do is use the 95% rule with the 2 tail and say, okay, let's grab the middle 95% of these averages. So what are averages of what? Well, what I did again is I created 6,000 new samples, all of 24 people. And I just wrote down in this chart here with Statkey's help, the average amount of screen time for each of those groups of 24 people. And Statkey found that looking at the middle 95% of that, the lowest average we see for a group of 24 people is about 4.2, and the highest average we see for a group of similar people is about 6.7. So this is my 95% confidence interval for hours of screen time per day. I believe that for community college students, they watch between 4.2 and 6.7 hours per day, if I were just going to go to 2 decimal places. So let's make some notes on this, and I'm going to need a calculator. Now, another note, Statkey put, it says in the average of all of these averages is 5.37. That is close to the original sample. When it comes down to giving the estimate for what we think the population should be, we usually go with the sample mean, not the mean of all the Bootstrap samples. So these 2 numbers, this one and this one, will differ slightly. We typically default to using the one from the original sample. So let's take some notes. All right, so let's see, population of interest. Let's see, here I said the population of interest could be all statistics students or maybe just BMCC students. And I changed my mind again when I was talking here on the video, or all community college students in the US. That's reaching, but why not? So since I didn't mention what my population of interest was based on this sample, I'm going to guess at what it could be. And why are these reasonable guesses? Well, remember, a sample comes from a population. So the group of people that I collected these numbers from, they're a sample. What population did I sample them from? Well, you all are part of lots of different populations, right? You are 24 of all of the community college students in the US right now. You also happen to be BMCC students. You also happen to be statistics students. So you are actually part of lots of different populations, and I think I'm going to go for this one as my choice for now. All right, what's my parameter? So a parameter is something we want to measure in the population, and we're using our sample statistic to estimate that. So our population parameter here is the average number of hours per day of screen time college students, community college students do. So the parameter, or more specifically population parameter, of, let's see, I think I should say screen hours Right, so that's what I'm trying to measure here. And based on my sample, I think that's about 5.375. So I could just state that. Say have about hours of screen time per day. Okay. Now again, I didn't ask everybody in all community college students in the US, so this can't be accurate. So then I have to come up with a margin of error. So the margin of error comes from basically measuring from the center out to the edge. So I think the average is about this, but it could be as low as 4.2 or as high as 6.7-ish. So first I'm going to get a screenshot of this, and screenshots differ depending on the kind of computer you have. On my computer, I search for screenshot, and I get the screenshot tool. Oops. You might use the snipping tool if you're on Windows, or if you're on a Mac, it's Control-Shift-4 or something like that. If you're on a Chromebook, it's something else. So learn how to take a screenshot on your computer, and I want a couple things here. I want this right here, because this represents my Bootstrap confidence interval, and I'm just going to copy and paste that into my document. Boom. I also think I want these summary statistics here, so I'm going to screenshot that too. That up here, there. Let's put that right after the question. And let's tone that one down a bit. And let's make this one a touch smaller too. No, it's fine. Okay, so let's calculate the margin of error. So given that a Bootstrap confidence interval, given the randomization of it, isn't necessarily symmetric, instead of measuring from the middle to the edge, either side, I'm just going to measure the whole distance across and then divide by 2. So I'm just going to whip out a calculator to do that, to get my margin of error. There's my calculator right there. All right, so I want 6.667. And every time I do this, it's going to be slightly different. I'll demonstrate that in a second, but it's going to be close enough. 4.188. So that's the distance across. And then we divide that by 2. So I get a margin of error of 2.2395. If I stick with 3 decimal places, that would be 1.240 for the margin of error. All right, so back here. All right, so I'm just going to make a note. Margin of error is about 1.240 screen hours per day. So that's how far off I could be. So I think the national average is about 5.375, but it could be 1.24 lower than that or 1.24 higher than that. So another way to state that, and I'm going to make this one a little more formal. If you look at the examples in the book of interpreting a confidence interval, they all start with I am 95% confident, or I am 90% confident, or 98, whatever the confidence level is. In this case, we're using a 95% confidence level, which represents the amount of subsamples that I grabbed in the middle, and my screen went blank there. Let's refresh and do that again. We'll come back to that. All right, so I am 95% confident that the average screen hours, you got to be specific, per day of community college students is between, it was 4.128, no, 188, yeah. 188 and 6.667, I think it was. And I don't need to put hours again because I already got that right here. Boom. So sometimes when you read information like that, they'll say, hey, we think the average is between here and here. Otherwise, they'll just say, we think the average is about 5.4, but then you have to read that there's a fine print somewhere that says, oh, by the way, the margin of error was this, in this case, 1.24. And that's about it. So let's just go over this again. To do a Bootstrap confidence interval, you got to have data. So here's my data. So copy your data wherever you got it, and then go to Statkey. And you want to be in the confidence interval for a mean. We also are going to do confidence interval for proportions this week, and you're going to edit in your data. So I'm going to delete their data, paste in my data, verify I have a header row there and no first column identifiers. And then once that's in there, double check you've got the right sample there and generate 5,000, 6,000, maybe more. And then you're always going to do a two-tail. And we typically will use 95%, but you'll have some problems that'll ask for like a 90%. So you might enter 0.9 there. And this program is using up a lot of my processor power, so it's lagging just a little bit. So if I'm on the 90% confidence interval, my 90% confidence interval would be like 4.4 to 6.4. But I want a 95% confidence interval. So this time it's 4.229 to 6.668, right? To two decimal places, or to one decimal point place, 4.2 to 6.7. It's the same as it was before. And I mentioned again, because of the randomization, this is generated from the original sample, like drawing cards from a deck. It's always going to be a little bit different, but the numbers should be similar. All right, let's see, what else do we need? Oh, side note, this question I asked on the syllabus, but I also gave an average person survey. And in this one, I asked average TV, hours of TV each day, video shows movies. I got very different answers on this one than that other question. So whereas the syllabus question that you saw a minute ago, average was about 5.4, the survey question, the average ended up being about 2.3-ish. Whoa, that's quite a bit different. Oh, I thought of another question. How does this compare to the rest of adults in the United States? So I did a quick search here, US video hours per day, and Google's AI overview said they found some places in 2023 that said it was about 4.5 hours per day. So if I was going to say, well, let's just say these are, US adults, because you guys are US adults, I could use you to try and estimate the hours of TV per day or screen time a day of a US adult. And this one down here says 3 hours and 50 minutes. And again, I should probably go to where they came from and get a little bit more information about that. But let's say, yeah, we think it's about 4.5. Is that in my interval here? And the answer is, yeah, it is. Okay, so let's suppose somebody like in the census where they talked to almost everybody in the United States and they actually got screen time data and they said, yeah, in the census we found it was 4.5 hours, then our little sample of 24 captured that in there. Does that mean your confidence interval will always get what the population value is? The answer is no. In this case, we're saying that 95% of similar samples will make another interval, there we go, that actually contains the population mean, but we never know if ours is one of those intervals. Okay, so this is tricky stuff. In some ways, conceptually, but in other ways it's pretty straightforward. We get our data, we plug it into Statkey, we generate, two-tail, and then there's our confidence interval at the bottom. Okay, so one more note on this, and we'll be good for now. This does happen to contain one publicized average of 4.5 hours per day. But there was another one that was 3 hours and 50 minutes. That one ain't in my interval. Okay, so according to one other survey I found online, the national average is about 4.5 hours per day, which means you guys watch a similar amount of TV per day. There's another one that said the average is 3 hours and 50 minutes. And in that case, based on this particular set of data, that means my students watch more than the national average. But then again, it may depend on the way the question was worded. So I should probably dig deeper on these two to compare their questions to my questions, because even my survey question had a mean of 2.32 hours versus the syllabus question had a mean of 5.4 hours. That's quite a bit different. Interesting. Neither of them are lies. They are the truth according to the data we collected. Humans are interesting critters. Keep up the good work. Do good math. I'll see you soon.